You know, in the world of AI, the race has always seemed to be about getting bigger. More data, more parameters, more computing power. But what if that's the wrong race entirely? What if the key to smarter, more powerful AI isn't about size at all, but about its shape? Okay, let's dive into this, because we are about to explore a pretty radical new idea that could completely change how we build intelligent systems.
So yeah, this is the big question we're tackling today. We're so used to thinking that making an AI more powerful is like building a bigger brain. But what this new research is suggesting is that maybe our current AI models don't just need a bigger brain, they might actually need a differently shaped one.
So let's frame this. On one side, you have the old way, right? The brute force approach. Just keep piling on more layers, more parameters, and hope for the best. But on the other side, we have this new, much more elegant idea that real intelligence emerges when you build an AI with the right internal geometry, a shape that actually fits the kind of information it's trying to learn.
To really get why this matters so much, we first have to talk about a fundamental flaw that's lurking inside most of today's AIs. It's a problem that researchers are calling the geometric capacity bottleneck.
So what is this bottleneck? Well, at its core, it's a mismatch. See, current AIs, they process information in what's essentially a flat space. The mathematical term is Euclidean space. But complex information, like language or all of human knowledge, isn't flat at all. It's hierarchical. It has all these branching structures, and that creates a massive fundamental incompatibility.
And this is the perfect way to picture it. This over-squashing is a huge reason why large language models can sometimes just make stuff up or fail to generalize what they've learned. They are literally trying to cram this huge complex tree of knowledge into a space that just wasn't built for it. And when you do that, the information gets totally distorted.
Okay, let's look at the math here because it really tells the story. In a flat Euclidean space, the volume only grows polynomially. It's awful at handling tree-like structures, and it causes a ton of distortion. But now look at hyperbolic space. This is a curved space. Its volume grows exponentially. That makes it absolutely perfect for embedding those branching trees with almost no distortion. I mean, the math is crystal clear. It is simply a much, much better fit for the job.
So, if the problem is a flat container, the solution is, you guessed it, a curved one. And this brings us to the hero of our story today, hyperbolic geometry.
Now, I know, it sounds a little mind-bending, but just picture a Pringles chip, or maybe a piece of coral. It's a surface that's constantly curving away from itself everywhere. And because of that negative curvature, as you move outwards from the center, there's exponentially more room. It is the perfect environment for that giant oak tree of knowledge to spread all its branches without anything getting squished. Now, the fancy theoretical framework for actually building an AI in this new kind of space is called a geometric control manifold, or GCM for short. And it's not just about using any curved space. It's about creating a really structured, stable environment where the AI's mind can operate, all governed by a very specific set of rules. And these are the 3 golden rules that keep that GCM stable. You can almost think of them as rules for a healthy mind. First, integration. This just makes sure the AI's thoughts don't fragment and break apart. Second, coherence. This ensures all its different parts are working together, in sync, instead of fighting each other. And third, differentiation. This makes sure it can hold on to a rich variety of complex ideas, preventing it from just collapsing into one simple thought.
Okay, so this all sounds amazing in theory, right? But how in the world do you actually build one of these things? Well, let's get into the blueprint and see how this all comes together in a working model they call the toy Psi-SLM.
This quote from the research paper is really the project's guiding star. It just perfectly sums up the entire philosophy here. Stop trying to just scale up. Instead, build a smarter foundation by matching the AI's internal geometry to the actual shape of the knowledge it needs to learn. It's all about shape over scale.
So at the very heart of this system is this single, incredibly elegant rule. The researchers call it the principle of least geometrocognitive action. And you can really think of this equation as the fundamental law of physics for this new kind of AI. Its entire existence is driven by one single goal: to minimize this action.
So, what does minimizing action really mean in plain English? Well, it breaks down into 3 pretty simple goals. First, L-task. Get the right answer. Simple enough, just like any other AI. But, and this is crucial, it also has 2 other goals it has to balance. L-geo, stay on that special curved surface. And L-topo, maintain your internal structure, don't fall apart. It's this constant, delicate balancing act.
All right, now for what might be the most important part of all this. Is all this geometry stuff really necessary, or is it just a fancy add-on? Well, the researchers designed a brilliant experiment to prove that geometry isn't just correlated with success, it's the cause of it.
They set up a direct head-to-head comparison called the divergence test. It was a classic A-B experiment. They built two identical AI systems. For System A, the experimental one, all those geometric and topological rules were turned on. For System B, the control, those same crucial rules were turned off. Then they just let them both learn and watch what happened.
And the results? Well, they were staggering. The geometry-aware system, System A, was 69% more efficient at learning, and even more importantly, its ability to generalize to new information it had never seen before, which is a key measure of true intelligence, jumped by over 23%. It wasn't just a little better, it was fundamentally more capable.
And this right here is the scientific knockout punch. The experiment didn't just show that the systems got different scores, it showed that they went through something called structural divergence. They literally evolved into two fundamentally different kinds of systems. The control system basically collapsed while the geometric one maintained its rich, coherent structure. This proves that the geometry isn't just helpful, it is causally necessary to get that higher performance.
Now, this isn't just some abstract experiment locked away in a lab. No, this new geometric approach is already being connected to real-world AI models and tools that people are using today.
Through a tool they call the SLM bridge, this geometric foundation can be connected to small language models that you might even recognize, models like Tiny Llama, Phi-3, and Qwen2. So this means we can start enhancing existing models with these powerful new principles right now.
And that opens the door to some incredible practical applications. We can use the SLM bridge to make existing models way more efficient. We can build something called hyperbolic RAG systems. Think chatbots that can understand the deep relationships between documents far, far better. And we can create more robust AIs by blending knowledge from different sources in this geometrically sound way.
Which brings us all the way back to our first big question. For years, we have been obsessed with scale. But maybe, just maybe, the next great leap forward in AI isn't about building bigger, flatter models at all. Maybe the future of AI is curved.